Hello everyone, welcome to Vocabulary of Physics. In this video, we are going to discuss about another fundamental concept, energy. Let's get into it. So first of all, like any other fundamental concept, defining energy is also a little complicated, little roundabout. First, let's try to understand what energy does to a body. Whenever you give energy to the body, what would happen to the body? So one thing is that it can move, having a kinetic energy, or it can be deformed, stretching, compressing, twisting, bending. So having a potential, deformation potential energy or elastic potential energy, or it may get heated up by giving thermal energy. You can change the temperature of the body, or it can also change the state or composition, solid, liquid, gas, or otherwise. Chemical composition itself can change when you have energy transaction, and energy can also change the mass. According to mass energy relation, you know that whenever energy is given, mass can be created and vice versa. So mass will change, but the variation is so small that in daily life, you will not be able to identify that. Okay. Now, if you look at a universe, observable universe, and the entire thing will be only two parts. Universe will have only two things, either energy or matter. A matter can be converted into energy and energy can be converted into matter according to that relation. And one important distinct point is energy can exist without matter in space in the form of electromagnetic radiation or gravitational potential energy and other forms of potential energy. But matter cannot exist independently because matter itself is a form of energy. So that's important aspect for us. The next thing is, let's read this particular statement given by one greatest professor of physics, very inspiring teacher. He says energy is a number that is conserved, and one of the first things you learn in physics is that energy is conserved. It is a kind of a strange number which we can use to keep account of how the things will behave, but it is in the end a sort of an abstract thing. That's what Richard Feynman says. So energy is basically abstract thing. It is a number, mathematical number, but it actually determines how the things will turn out in a particular situation. So that way we have it. Now let's go to the definition of energy. When we define energy, you have to define work also simultaneously. Any standard book, if you look at it, it is defining like this. Energy is the ability to perform work. And what is work? Work is the transfer of energy. So work and energy have to be defined simultaneously in terms of the one another. So that's the way we have it. Just to understand it, let us take one example. Imagine you have steam or combustion gases or water or wind, something having a kinetic energy flowing into this turbine. This turbine or rotor will be rotated because of this kinetic energy. So this kinetic energy will perform work on it to change its kinetic energy. So that kinetic energy will get transmitted to the coil here. Because of that, the coil will rotate in magnetic field, which produces electric energy. So if you observe it here, energy is doing work here, and this work is converting that kinetic energy into electric energy. So energy is ability to do work, and work is converting one form of energy to other form of energy. That's how we need to understand. So if energy does not interact with matter, there is no way we can define energy as such. It has to interact with matter and see how it behaves. Accordingly, we'll be able to define that energy. Nevertheless, finally, what is the working definition of energy? How do you understand that in a very simpler terms? Energy possessed by an object, energy contained by an object, is its capacity or its ability to move things or heat up the things. That's a basic idea. If you understand this particular definition, you will be largely able to follow the idea of energy in any basic understanding of level. Let's get into some more examples. So what is energy in daily life? There are many examples related to kinetic energy, things moving. There are potential energy, gravitational potential energy in these two cases, and deformation potential energy in these two cases. And you also have thermal energy, where heat is given, and then you have various situations that you will observe the thermal energy. And also you have electrical energy, light bulb and fan rotating and so on. Electric energy is given. Also, we deal with magnetic energy, in that especially this particular one, maglev trains, magnetic levitation trains. So they actually move almost floating, like friction is almost neglected. They go with very high velocities. And headphones and all these are all magnetic effects that you want to study. In addition to that, you have chemical energy where you have gases and petroleum, which can be burned or combustion process to produce thermal energy. Photosynthesis, where the light energy is used for some particular chemical composition. These are all chemical energies that we deal with. So these are all types of energies. There are so many names to them depending on how they are being used. But when we go to physics, all these types of energies can be simplified into a very simple categorization. Total energy can be divided into two parts. Energy which is contained in the matter, energy which is contained in space. Energy which is contained in the matter is further divided into two parts. The energy which is contained in the matter can be used for movement of the body, kinetic energy related to energy of movement, which has got again three variations: translation, vibration meaning up and down, okay, or back and forth, and also rotational kinetic energy. These are the three different kinds of motion you will have. Anything other than translational, vibration, and rotation contained by the body will be called potential energy. And if you go for the energy which is in space, basically electromagnetic energy, gravitational energy, these are the primary things that we study in large scale. Microscopically, you may have strong nuclear forces and so on, but macroscopically, these are the things that we have here. Okay. And when you go for a very large scale, going for the stellar situations, what are the energies that you will see? Primarily this fusion energy, nuclear energy, because of the nuclear fusions, huge amount of energy will be liberated in the form of thermal energy. Electromagnetic energy, it is a small part of it, radiation coming from stars and so on. Gravitational energy, whenever mass is present, there is a gravitational field around it. That field corresponds to gravitational energy. Rest mass, as you know, it is related to E equal to mc square, where mass can be converted into energy and so on. These are the forms of energy that we have. Apart from that, this is dark. Something, still things are being in a hypothesis mode. We have not been able to establish these things, dark matter and dark energy. I'll not go into the details of it, but this is what we have at cosmos level. Now, if you usually I go with the history, here also let us go into the history of how the things have gone. The first one is Leibniz, who has worked on this, contemporary to Newton. Newton was focusing on linear momentum. That was what he thought was the most important factor. But he thought mass times speed square, which is double the kinetic energy, is something related to energy which is expected to be conserved by him. So that was the first time where we have seen something similar to energy has been proposed by a scientist. And after that, we have Thomas Young, who has done a lot of work along with the other great scientists. So he has proposed actually the basic idea of energy that we use now. Energy concept has been established after Thomas Young. And we have another scientist who had translated Newton's work. And Charlotte is very famous about mathematical acumen that she has. She was the one who has hinted first time about the conservation of energy. So that is another important milestone. And after that, we have Joule, who has worked a lot about thermal energy. He is the one who had given the link between work and heat. Until that time, heat was considered to be some other physical quantity, different from energy. But he has proposed or established the fact that energy, work, and heat, all of them are interrelated. Both of them, all of them will have the same unit on his name, Joule, in SI. Now, energy transformation. Energy will always be transforming from one place to the other, one form to the other, chemical to mechanical, chemical to light energy, electrical to light energy, chemical fuel, when you burn it, chemical energy will be converted into mechanical energy and so on. So transformation is happening all the times. Transformation of energy is one important phenomena that we observe. But if you observe it very carefully, one type of transformation is very easy, very likely, but the reverse process may not be that easy. And that is what second law of thermodynamics talks about. It's related to entropy. Any process where entropy increases is natural phenomena where the energy can flow in that direction very easily. To go in opposite direction, some additional work is required. So that's what it says. For example, this fuel can be used to convert that into mechanical energy. But converting mechanical energy into fuel is not an easy process. That's not naturally possible according to second law of thermodynamics. So now when we study about this transformation, Is it necessary that energy has to be conserved? Only form will change. That's what you will get basically. That's where this discussion had come. Right now, this principle of conservation of energy is very, very important cornerstone in entire physics. And on this, the first one who had worked and who has given a basic idea of conservation principles is M.E. Noether. She's a mathematician. She has done a lot of work on transformation, matrices and all that. So whenever there is a symmetry of time correspond to energy conservation, symmetry of space correspond to conservation of linear momentum. She says that whenever there is a symmetry about physical laws, some conservation quantity has to be there. That's how this conservation of energy has been proposed mathematically with a very established theoretical backup there. So once this principle has been established, it has been applied in many places. When you study physics, you cannot miss conservation of energy. Hamiltonian is basically energy, total mechanical energy. Bernoulli's theorem is direct application of principle of conservation of energy. First law of thermodynamics is basically conservation of energy applied to any thermodynamic system. Kirchhoff's law, circuitous law. So there we say that electric field is conservative field, there the energy is conserved. When you come back to the same point, you will have the same potential. That's also basically conservation of energy. Lenz's law is direct application of conservation of energy. Induction opposes the cause. Consequence of conservation of energy. That's what we talk about. Other things also. So there are many things, numerous number of things where we'll be able to explain that particular idea using the principle of conservation of energy. So now concept of energy, when we go to relativistic view, as we have been discussing, mass can be converted into energy. But more importantly, this one, energy and momentum connection. That's very important here, where Newton has worked on momentum a lot about. So whenever there is energy that is associated with momentum, especially when it is energy of movement. So momentum corresponds to kinetic energy. With that idea, this particular postulate has been given. Even if the particle is massless, if that particle contains energy of movement like photon, it will be able to exert momentum. That is very interesting idea that we have here. So where is this impact here? You have impact all over any part of the physics, nuclear physics, particle physics, astrophysics, where we'll be dealing with high amounts of energies. This is a very important point we have. Finally, at update level, if you see, is energy really conserved? It is said that energy is not really conserved. How is it? So when we look at that Noether's theorem, in that Noether's theorem, one important condition is that space is supposed to be static. But we know that space is expanding. The separation between any 2 points in space is increasing. Then obviously energy cannot be conserved if that is the situation. Imagine you have a radiation with a wavelength lambda naught. When the space is stretched, when the separation between these two things increase, then obviously wavelength will increase. When wavelength increases, energy of the photon will decrease. It's not conserved. Energy is not conserved. So energy is not conserved. That is true. But is it really such an important effect that we see? If you want to observe this kind of changes, appreciable changes of energy of photon here, you will have to wait for millions of years, which is far beyond our human related scales that we deal with. So for our all practical purposes, conservation of energy violation can be neglected. We can assume that the space is not moving at all. Under that idea, we can use conservation of energy very comfortably. So that's what about this particular video. I hope you understood everything. We will come back again with another interesting video. Until next time, goodbye.